we are going to discuss about the initial phase. Okay, the initial phase part is very, very important that we are going to discuss. Suppose one particle has started its journey from this point. Okay, one particle has started its journey from this point, and let this angle is, let me take it as phi. Okay, and after some time it has reached to this point like this. Okay, this is the point. Okay, here it has reached. Okay, so this total angle from initial point to the final point, the calculation will be your omega t. This total angle is omega t, right? So if we are going to calculate from the mean position, if suppose we are calculating from the mean position, what is the mean position? This one. Okay, this line, right? So if this is started from the mean position, that is the 0th position from here, okay, at this point, okay, now the calculation will be, what is the total angle? If I am going to calculate this one, this is the foot of this one, right? This is the final. Okay, this one is the final one. This point is the final one, right? So this to this, I will draw a foot. Okay, this is the final point. I will draw a foot like this. Okay, and here this is y. Okay, so this one is also y. Okay, this line is also y. So if I will calculate this y, okay, then y will be of the formula a sine, okay, formula is omega t, right? The normal formula is what? A sine omega t. But here simple change is there. What is that? We are calculating from the 0th position to this final position, right? Or from the mean position to this position. What should be the angle? This is the angle, this small angle, right? So what is this small angle? Big angle omega t minus of small angle phi. Okay, this will give you this angle theta. Okay, this angle theta, right? So this is nothing but omega t minus of phi. Understood everybody? Yes or no?
Yes, sir.
Yes or no, everyone? Switch on your mic and say me yes if you understood.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now suppose if we are going to start, or the particle has started from a point here, okay, at an angle phi. Okay, it is started at this point. Okay, at this point. Now it is going to this point. Okay, this angle is omega t, particle to particle. Okay, initial point is this, final point is this, is going, so this angle is taken as omega t. Now if I am going to calculate from the 0th position or the mean position, this is the mean position, okay, mean position to the final position, right? What is the final position? This point is the final position, right? Then what should be the formula? Again, y formula is what? Take a foot like this. Okay, this is y, this is called as y, this is the position, right? And if I'm going to calculate this one, this y formula is nothing but a sine which angle? This total angle. What is this total angle? This total angle is nothing but what plus of what? Phi plus of omega t. This formula is y equal to a sine omega t plus of phi, right? This is what? Omega t plus phi is the total angle theta. Okay, because where to where I want to calculate? From this point to the final point, this point. This angle is theta, right? So this theta angle is right now what? Omega t plus phi. Omega t plus phi. This phi angle is known as the initial phase. Okay, so this is known as the initial phase, right? So now let's move on to the next part, that is our next chapter, known as waves. So what is a wave? Wave is a pattern of disturbance created in a medium which carry energy from one point to the other without transport of the medium. Okay, so what is a wave? It's a pattern of disturbance created in a medium which carry energy from one point to the other point without transport of the medium. For an example, here suppose I can say here a rope is being attached, okay, to a rigid surface like this. You are placing your hand or fingers at this point, okay, you are taking this one and you are vibrating this one, okay, you are just disturbing this one, okay, this particle at this point. At this point you are disturbing up and down like this, okay, and you will observe a pattern is moving like this to the other point, okay. This rope is not moving, okay, the rope is not moving like this, only a pattern, okay, the pattern is traveling to this direction, okay, towards this direction. So that is what a pattern of disturbance is, transferring from one point to the other point without transfer of the medium. Means this rope is not transferring. Who is transferring? Only the disturbance, right? So this is known as the wave, okay, this is known as the wave, okay. It's a pattern of disturbance. And one thing I told that you people has to remember, okay, that is what, if this is the rigid surface, okay, if this is the rope, and what we will do so that a wave is going to travel, you have to vibrate, that is what, oscillation, okay, continuous oscillation of this particle, okay, of this particle will allow the disturbance to flow in this direction, right? So this is what, creation of wave. So who is responsible? Oscillation is responsible for the creation of wave, okay. So oscillation is responsible for the creation of wave, okay. So if we are going to calculate for the full wave how it is going to be produced, see here, suppose this is the particle here, okay, you will oscillate at this point, okay, so this is the neighboring particle, this will rise up, okay, because of the pushing force, right? Here also it will also apply a push force, because of that again it will rise, then this point will rise, okay, then this point will rise like this, so the wave will start to flow like this, okay. So this is the complete phenomena of the wave structure, and you can say the wave is created due to oscillation. And I have also given the example, wave is also created due to oscillation. Take a point of ribbon attached to a fixed point and oscillate. You can observe one pattern of wave is moving from initial to the final point, right? And on the basis of disturbance, wave is classified into two types, okay. There are two types of wave are being classified to, okay. One is known as transverse, another one is known as the longitudinal one, lengthwise, okay. So first look at to the transverse wave, the same one that I have given the example. You are oscillating this one, okay, at this point. So oscillation is happening in this direction, okay, and the wave is traveling like this, okay. The wave direction is this one, traveling of wave, the distance traveled by the wave in this direction. See here, oscillation in this direction, okay, the wave in this direction, both of them are perpendicular to each other, okay. So this kind of wave is known as transverse wave, where oscillation and traveling of wave are perpendicular to each other, right? Next is a longitudinal wave, okay. What is a longitudinal wave? See, if you are compressing something, okay, this is a material like this sponge kind of material, you are compressing at this point, okay, you are doing a compression at this point. This compression is going to travel from this point, then to this point, then to this point, and at last it will reach to the last point, okay. So here the disturbance is moving in the lengthwise manner, from this then to midpoint and then to last point, okay. As it is going from the lengthwise, that's why it is known as the longitudinal wave, okay. Where you are oscillating, your particles are oscillating in this direction. Okay, and where the wave is traveling, the wave is also traveling in this direction. How much angle they are making? 0 degree, right? So oscillation and wave traveling are making 0 degree to each other, right? Here you can say, here wave and oscillation direction are same, making an angle 0 degree. Okay, what is that called as? Longitudinal wave. Now let us read what is the quantities related to the wave. Before that, let me tell you what is the full cycle of wave. Here is the particle. Here you will reach it from the mean position to the topmost position. Okay, so one crest will reach, right? Then when you will come back to the mean position, okay, it will go to the 0th point. When you will go to the negative maximum, a trough will arise, right? Then again when you will reach to the 0th position, you will reach to the 0th position here, right? This is known as the full cycle of your wave. Okay, and that is what? Full cycle of oscillation. Okay, so one full cycle or one complete oscillation is equal to one full wave. Okay, and this will repeat again, crest, trough, like this. Okay, so this is the quantities, you can say, or you can say this is the complete phenomena. Okay, complete phenomena involved in the wave process, right? This is known as the crest and this is trough, right? And you know it how to find out from the figure. Now next is how to find out the wavelength lambda. Okay, how much the wave has traveled. Okay, wave's length is known as lambda. And what is its calculation? From two successive crests. Okay, the distance between two successive crests is known as lambda, or between two successive trough is known as also lambda. Okay, and what is this one? This is a full time. How much time it has taken? 0. Okay, this time is t by 4, this time is t by 2, this time is again 3t by 4. Okay, and the last one is t. Okay, so what is the full cycle of your, what you can say, or the full wavelength lambda? Full wavelength lambda will be completed in time capital T. Okay, and capital T is the time from which phase to which phase? 0 to 2 pi. We have already studied this one in oscillation. So lambda will be completed in the time capital T, that is at 0 to 2 pi. Okay, so that's why one cycle of wave is equal to one oscillation of the particle. Here it is written clearly, one cycle of wave is equal to one oscillation of particle. Moving on to the next part. Let's see the quantities again. Here you will mention, instead of frequency F symbol, you will use your nu. Okay, this is the new symbol for the frequency. Time taken is capital T for one cycle. We all know nu is the frequency, lambda is the wavelength. That is what? Distance between 2 points of the same phase. That is 2 successive crests, okay, or 2 successive trough. Okay, that is known as the lambda. And let us calculate the propagation constant K. What is known as the propagation constant? Okay, lambda length. Okay, lambda length, wavelength, phase change. How much phase has changed for the lambda length? 2 pi. Just now I told 0 to 2 pi, because the time taken is 0 to t, so the phase will be of obviously 0 to 2 pi, right? So 1 unit length phase change will be how much? For lambda length, if the change is 2 pi, for the unit length the phase change will be 2 pi by lambda. Okay, 2 pi by lambda. This is known as the propagation constant K. Okay, so the wave is propagating, and this is 2 pi by lambda is known as the propagation constant K. Okay, and how I can find out the velocity? The velocity I can find out by simple formula, distance upon time. Here distance is what? Lambda, right? Lambda is the wavelength traveled, and time is what? What is the full time covering? Capital T. Okay, so 1 by T is known as what? Frequency. and frequency we are writing with the symbol what? Nu. So this is lambda into nu. Okay, lambda by t or lambda into nu. Okay, now moving on to the equation of waves. Okay, what I can write it in the equation of wave. Okay, the quantities involved, you know it. A equal to amplitude, k equal to propagation constant, phi equal to initial phase, just now I told, okay, in the beginning of the class, lambda wavelength, v velocity, y displacement of the particle, and x is the distance traveled by the wave in the small time period t, or in the instantaneous time. Okay, in what instance the wave has traveled up to what position, right? And the wave equation is a combined formula of the two form, that is where the time is constant, another one is where the displacement is constant. Acha, now when the question will come to your mind that how the time is constant, how you can make the time as zero. Simply you are watching a sea wave is going like this, okay, in some sea beach or something else, you will take a snap. Okay, then at that point the picture is captured like this. Okay, now if you will calculate here, the time period is what? Obviously constant, right? So obviously you can make a time constant. Where? In which device? Obviously with the help of any snapshot, right? Next, displacement. How a displacement is constant? Suppose I can say this is a river or something else like this, okay, and the waves are traveling like this, okay, and at this point one wooden structure is present. Okay, then neither I will see from this side nor I will see to this side, only I will check to this wooden particle. What is happening with this wooden particle? Whenever the crest comes, this wooden particle is moving to upward direction. Whenever a drop comes, it is going down. Okay, so what is happening here? Simply a oscillation. Simply a oscillation of the wooden particle. And here what I have done, the displacement, okay, I made as constant. As the particle is moving, no, what is happening? Only a oscillation. Okay, this is here in this point I am not calculating the, or I can say the displacement I have made as a constant. I am not interfering on the distance. What I am interfering only? I am only considering the oscillation, only a crest and trough, okay, at a single point, crest and a trough at a single point, okay, at a single point, right? So this calculation is known as the where the displacement is constant. Okay, this is a full wave, okay, but what I am calculating, crest and trough, only at the particular instant, right? And what I am considering here, only the oscillation. Okay, so where the x is constant, when, okay, at that time when the x is constant, the displacement is constant, at that time what is happening? Only the oscillation, right? And for the oscillation, if time period is there, we know the formula and we have derived in the oscillation chapter, no need to derive it again. Y equal to a sine omega t. Okay, now the next formula is, if the time period is constant, then the formula is, for the snapshot I told, if you take a picture, click a picture, the formula is y equal to a sine kx. Now let's see how the formula is y equal to a sine kx. Let's see the formula clearly. As you can see here, we know the formula y equal to what? A sine omega t. Okay, because we are doing a oscillation and here a wave is going to be produced. Let's take y equal to a sine omega t. So lambda is the wavelength which is going to travel at time capital T. Lambda is the wavelength, okay, is going to travel at a time capital T. Okay, now a unit length, okay, if the lambda length, or you can say lambda wavelength, is traveled in time capital T, then 1 meter, okay, 1 unit is going to be traveled at time, or you can say at what? T by of lambda. The calculation will become for a unitary method T upon lambda. Okay, so lambda length will be covered in time capital T. Okay, so 1 meter will be covered in time T upon lambda, right? So x meter, okay, x meter is what? Suppose this particle is here, okay, this is the wave, okay, and this to this is 0th point, and this point is suppose x, okay, this is the point is x. So here to here only it has traveled, okay, here to here only it traveled at time small t. So this calculation is for what? Small t. Okay, so x distance will be covered t by lambda multiplied with x. Okay, and what time it will be covered? Small t. So this will be the calculation for the equal to small t. That one was for the capital T lambda calculation, and for the x, x means what? For a small distance covered at a small time interval t. This is the calculation, right? So small t. So here what is the small t formula? T by lambda into x. Now what I will do it here? Y equal to a sine omega t. What is the formula? A sine omega t. Here I will place the formula in the t. What is that? A sine 2 pi by t. Okay, omega value is what? Omega value is 2 pi by t. Just place it here. 2 pi by t omega into t value is how much? T value is just now we found small t value, t by lambda into x, t by lambda into x, right? So what I will do here, t and t cancelled. Okay, so what is the formula? 2 pi by lambda into x, 2 pi by lambda into x, and here you can see what is 2 pi by lambda? Propagating constant k. Okay, so the formula is y equal to a sine kx. Okay, so the formula is y equal to a sine kx. Here is the formula. Okay, so the formula is when the time period is constant, then formula is y equal to a sine kx. Okay, if both will vary, we will get a combined equation. Okay, what we will get? We will get a combined equation, and that formula is y equal to a sine kx minus omega t or plus omega t according to where the wave is traveling. That we will discuss it later in the next class. Okay, so let me stop